Welcome to the lecture on flow analysis in Tundish. So, now we will see that how the modeling work is carried out for the flow analysis in Tundish, and how you can show the flow behavior of the liquid metal inside the Tundish. Because the inlet through the inlet the liquid metal enters, and then it is going to all the outlets. So, once striking, first of all it will strike at the Tundish bottom, and then from there it will move gradually towards the outlet or outlets in the case of multi-strand Tundish. So, now in that case, as we had discussed that the methodology for the flow analysis is that you have to create a geometry of significance where you want to in which you want to have the flow modeling to be carried out. Then you have to select those parameters, like what is the inflow rate into the Tundish, and what are the boundary conditions, like if you are solving for temperature, then what are the conditions at the walls, what you are going to specify, and what are the other parameters like turbulence parameters, or maybe other things we have to set, like you have to go for the solution control parameters and all that. So, and after that our job is to have the analysis of flow inside the Tundish. So, so that is what we had earlier seen, that when we are solving a problem, in that case we first create a geometry, then we create the computational mesh for the geometry, and then set up the CFD simulation, and in that we have to set the material properties and boundary conditions. Then we have to solve the equations using the solver, and ultimately in the post processing stage we have to examine the flow field as well as the temperature field, and if we are solving for any scalar we have to see the scalar transport also that scalar field also you have to check it. So, so first of all as we discussed that we can take one geometry hypothetically, or we can have. So, on this I had done this simulation. So, in that what we see is that this is a typical Tundish, and as you see that this is the inlet, and these are near, middle and far are the outlets. So, this is typically a multi-strand Tundish. You have more than one outlet. So, then we call it as a multi-strand outlet, multi-strand Tundish, because you have more number of outlet. We have given this nomenclature near, middle and far because it is near to the inlet, that is why. Otherwise it may be taken as outlet 1, outlet 2 and outlet 3 also. As you see that this is the length of the Tundish, and this is the height of the Tundish, that is 600 mm, all the dimensions are in mm. Suppose then this is 600 mm is the height, and 800 mm is the width, and then if you add, so it will be 2200 plus, so it will be 3 meter, 3000 mm is the half length of the Tundish, and it is the symmetry plane. So, it means symmetry plane means the half of the Tundish is extending towards the left side also. So, your that way your whole Tundish length becomes 6 meter. Then the outlets are placed, as you see it is near to this wall, it is not in the middle. So, had it been placed inside the middle, we could have even taken the 1/4 of the Tundish for the calculation, because that way that is the symmetry maintained. So, in that case you have to make this geometry. So, for that in normal any kind of modeling tool, you can create these geometries either by taking these points at different positions, and then you can join them to form edges, and then you can have the surface creation, and then you create the volume. Similarly, you will have to have these areas identified, like for the inlet and for the outlets and all that. So, that way we create these geometries in the Tundish. So, after we have created the geometry, then we have to mesh it. So, you can have a structured mesh, or you can have unstructured mesh using the using the computational tool. And in the structured mesh, you will be giving certain number of mesh in the x direction, certain number in y direction, and certain number in z direction. So, accordingly you will have a structured mesh, and in that as we have discussed, that the trait of that mesh is that you can have any particular point or any particular cell. So, they are represented by a particular value of I, j and k. So, or else you can have even unstructured mesh. So, for simple geometries you can have a structured mesh. So, if you do the meshing, and if you take these number of cells in the x, y and z direction, so accordingly you can have this kind of gridded domain. The domain is now filled with the number of grids, and it shows the control volumes which are formed because of the the number of meshes which have been taken in the three dimensions. So, you have a 3-dimensional geometry now, and it has also the grids. So, that way you get this structure. Now, you are going to set up the model, and before that you may identify the different different zones also inside. So, you can have the identification of inlet, outlets, then you have the different walls you can set as the walls, and also you can have the zone also as the continuum, or where the liquid is there, so that you can set it. Now, what you have to do is you have to set up the model, and in that if you are going for the heat transfer study also, you have to go for the enabling that energy equation. So, you have to solve the energy equation, or else you will write the equation of energy, and you will be using the standard K epsilon turbulence model. So, you have to write those equations if you are solving with your own handwritten code, or if you are using any computational code which is freely available, or it is available with you, then you have to select them. You can go for standard K epsilon turbulence model, or you can go for all different types of turbulence models which are available, like maybe RNG and realizable K epsilon, and other load Reynolds number models. But that depends upon the for simple type of flows, standard K epsilon turbulence model works better. So, we go for the standard K epsilon turbulence model. Then what we have to do is we have to set up the material properties. So, as we know that we are going for the steel. So, you can have these approximate value of the density, specific heat, thermal conductivity and viscosity of the steel. So, accordingly these values may be required for solving the equations. Now, when you are going for the boundary conditions, so in that boundary condition you will be having the option to take the values at those boundaries. So, you will have the inlet condition, and in the inlet as you know, if you know the casting rate, or if you know the mass flow rate which is going from the ladle to the Tundish. In that case depending upon the inlet diameter or inlet dimension, you can have the calculation of the velocity at the inlet. So, that is known as velocity inlet, and in that case you can calculate the velocity. So, if you know that mass flow rate, so it will be rho into A into V, and rho we know for the steel, and A is the area of the inlet. So, accordingly you can find the velocity. Then turbulence intensity, as we have discussed, we have the expression for the turbulence intensity, and that is defined in terms of percentage. So, and also it is basically representative of the turbulence, which is normally 2% to 5% value is taken, and it will be depending upon the fluctuating component with respect to the mean component of velocity in turbulence. So, we normally have it 2%. You can also have the length scale. So, length scale also, as we know, that it is normally 0.07 L or characteristic length of the Tundish. So, like that you can have those values. Now, as we know that we have taken the inlet condition as the velocity inlet, means we have given that velocity, particular velocity at the inlet, then you have the outlet condition as the outflow conditions, and there will be mass balance that will be maintaining, and the inlet temperature, if you are solving for the temperature. So, in normal case you take that inlet temperature value. So, that is we set some value. So, maybe if you have a metal which is entering into the Tundish of 1600 degrees centigrade. So, you can take the inlet temperature. Now, as you know that you have the heat flux that needs to be provided. Now, the thermal conditions include the boundary conditions at the walls, because from the walls the heat is being dissipated, and also from the top surface the heat is being dissipated. So, from the top surface it will be going to the atmosphere, and from the walls also there will be, we have discussed that there will be different way by which the heat will flow through the walls and then it will go to the surroundings. So, for a simple case you can have the heat flux from the free surface at the bottom wall, at the long wall and at the short wall of the Tundish. You can have those long wall means along the length, and then short walls are on the sides. So, from there you can have these heat flux values that you can take, and that will be required to study the temperature distribution, how the temperature changes. Now, when we are so as we discussed that we are applying the boundary conditions, and normally on the walls we apply the no slip boundary conditions, and we also use the standard log law wall function in the case of standard K epsilon turbulence model. So, in the standard K epsilon turbulence model you have to also be careful that the first grid where it should be placed, because we are not taking the low Reynolds number values, low Reynolds number flow. So, we are taking that to be a turbulent in the turbulent region. So, you will have to have the first grid in that zone, so that care has to be taken. So, and then in the thermal conditions you may have the different options, and you can take these heat flux condition as we have taken in this case. Now, when we talk about the wall boundary conditions, then many a times we can take the low Reynolds number models also, because they in the vicinity of the wall they take the condition that the flow to be laminar, and in that case you will have the more number of grids near the wall, and that is why they sometimes take larger time. They take larger time because once the number of grids will be more, in that case the time requirement will be more. So, that way your these wall boundary conditions are to be provided with proper understanding that what kind of model you are taking, and how that will be helpful in true manner the flow which is occurring inside the domain. So, so that is about the wall boundary conditions. Now, once you have set all these boundary conditions like inflow, outflow, wall boundary conditions, then you have the thermal boundary condition that may be given in terms of the heat flux value, or maybe you can provide a specific temperature also. So, that way it will calculate the heat flux value. In this case it calculates the temperature value. So, accordingly these values can be given, and then now before we start the solution, so we have to set the solution parameters. So, before that how we are going to take the pressure term into account. So, for that there are different algorithms, and then we use the semi implicit based algorithm, pressure linked equation. So, so that is used. So, you have simple, you have simplex, you have P. So, different type of algorithms are there. So, pressure is very important term, that minus dou P by dou x or dou P by dou y, that term is coming. So, we need to model that also. So, for that you have these different algorithms, and normally simple we take. So, you can have the from the drop down list if you are using one code, and then also there also you have to define that how you are going to discretize, take the discretization methods, maybe for the momentum, for dissipation rate, for kinetic energy, for energy. So, normally we can take first order or second order upwind discretization schemes. For them we had a certain idea in our earlier lectures. Then we are also taking the residuals, because the residuals they show when you have to stop the solution. So, basically that will be only when you feel that the steady state is reached, when there is change in value which is less than certain set parameter, set value. So, because in that case when there will be no change and you are setting that there is a change is less than certain value, then you are stopping. So, we are changing, giving certain values in standard codes, and then we get set these values, and you can have 10 minus 3 to 10 power minus 6 for these parameters. Then finally, we do the initialization for the starting of the solution, and then we start. So, normally we initialize from the inlet values, and values are initially provided, and then we do the iteration, and that iteration goes on. And when we are doing the unsteady analysis or steady analysis, in that case time is not involved. So, we give the that for how many iterations you have to start, we have to run the program, so that you get the proper flow field. So, if you run then you get this way the residual plots. So, as we see we have set the residual plots, and this way it will come, and after that, after some time, certain time, if the residual conditions are met, as you see, for continuity, for x velocity, y velocity, z velocity, energy, turbulent kinetic energy, epsilon is the rate of dissipation of turbulent kinetic energy, and then you have, if you are solving for even for the tracer or scalar quantity, in that case, that is also solved. So, that way on the monitor you can have the visual display, and then you ensure that the solution is complete. So, once you do that, in that, during that process, if the geometry is simple, it may take less time, but then in most of the cases it will take a large amount of time. Maybe sometimes the convergence rate is very small, or it is showing abnormal behavior. So, we have to choose the relaxation parameters also. Under relaxation parameters, in that case, that will be basically changing that how much taking you are how much in what way you are going to incorporate those changes for getting a proper meaningful result from the earlier iteration value and to the next iteration. So, that way these relaxation parameters are being used. So, that way this ensures that equation is properly solved and converged. So, then once you ensure that it is completely you are getting a converged solution, then you go to get the results. You can have the temperature contours as you see, and although it is showing 1.87 only 1870, which is basically the inlet temperature, but if you take the range, then it will show, or it tells that at here the temperature is maximum, and then you see that on the walls how it is slowly varying, and here it is minimum temperature on these corners, and it is decreasing as you see on the top surface. And on all the walls you can have the temperature contours that will give you the idea that how the temperature is changing all across the domain. Then the more important is to know the flow behavior of the steel inside the Tundish. So, as you see, these are the velocity contours at the inlet plane, and this is the velocity. If you look at the inlet plane, as you see, this is the inlet vertical plane. So, as you see that you have the flow which is coming on the coming in the bottom direction, and then it is moving from here. So, that way and it is moving through here, and then so basically it is a convective contour is shown. So, but then this way it is coming, and then it is going inside through that domain. So, velocity is high, and although it is less on this side. Now, if you take that outlet plane, so what you see that the metal now from here, as you see, this is toward the near the inlet, and once it has come, then the liquid metal has the tendency to move up. So, this way it is moving, and they are coming and going, passing through the outlet. So, this is how you can have the you can see the velocity of the liquid steel at these different locations, and the velocity contours can be seen. Maybe we can see also later that there may be a kind of loops also you can find when you use the flow modifier. So, that time it is more visible. But this is how you can see that there will be flow, and as you see that the liquid is passing through this at a very high velocity here, because being near to the inlet it will be passing, and then as the it is moving away from the inlet. So, certainly the velocity at which it will be approaching that will be certainly changing, because as you move away from the inlet, in that case the velocity will be changing. So, that is at the outlet plane. You can have also the velocity at the bottom plane. So, as you see the plan view, the liquid metal has stuck the Tundish bottom, and then it is spreading in all the directions. So, we are having a very high velocity there. So, it is moving, and then as you see that it is slowly the velocity will be changing, it will be the surface so it will be going from here, it is you have the first so you see that considerably large velocity is coming, and then you will have the metal coming through all these outlets. So, the velocity can be computed, you can see that where the velocity is high, where the velocity is low. So, these ideas can be obtained from these velocity vectors that can be drawn. So, the idea is that you can very well see the velocity vector and you can draw the thermal contours. You can also draw the contours for the turbulent kinetic energy, which will be indicative of the value of these parameters, turbulent kinetic energy, where it is higher. So, where you have given the velocity higher, you will see that your that values will be more. So, accordingly, because and then from these velocities you can have the idea also that what are those regions where the velocity is very small. Normally, if the velocity is very small in certain region, that may be a probable reason for the dead region, for the dead space, because the liquid may not the liquid which is coming continuously, that may not go into that zone, and so that may be the ineffective utilization of the Tundish volume. So, this can be seen from these velocity vector values. Now, we can see also that when we use the flow modifiers, in that case these velocity vectors change. So, what happens that as we have seen that when we start the solution, or when we start looking at the velocity vector at the bottom wall or even at the outlet wall, we see that near the outlet it is quickly entering. So, that is known as short circuiting also many a times. So, if the liquid metal will directly go into that, then the high temperature steel will not go into other zones, and in that case other zones may experience a smaller temperature. So, many a times what we do is we are to alter the flow modifier, flow configuration inside, we use the flow modifiers. Now, these flow modifiers may be in the shape of a dam which is placed on the bottom wall, which is its one position is at the bottom wall, at the bottom at z equal to 0, and it will have certain height. Suppose in this case it has a height of 225 mm. So, we may have a placement of dam just to ensure that the liquid metal which will be striking, then after that it will be deflected and it will go inside, and then it will have a loop. So, it will go into other zones, and the high temperature steel which is coming, it will be making all the zones also active. So, for that we use the dams. We also use many a times the weirs. So, weirs are basically used from here. So, we use from the top and at certain of certain height. So, that way we can also use the weirs in these cases, and then we also use the baffles. Baffles will have the limited outlet area in that whole domain. So, through that the metal will pass. So, dams, weirs, baffles, and even the advanced pouring boxes are Now it is designed which the boxes are near, I mean on the bottom wall and in just below the inlet. So they are there to see that what is their change on the flow alteration. So this is a bare Tundish with dam and Tundish with baffle. So if you take the velocity vector, you will see that there will be changes in the velocity vector. You will have, as you see that being the bare Tundish, you will have such kind of velocity vector, whereas if you use the dam, in that case the metal goes up and then you can see that the higher velocity is seen on this side. So you will have higher velocity, as well as if you use the baffles, you can see that it is how these are altering. So basically it will be altering the flow pattern, and then the so there may be different purposes for which the Tundish is used. Many a times we need that it should mix thoroughly, many a times we need a quiescent flow, quiet flow or so. So depending upon the situation, we can use these different flow configurations. If you look at the outlet plane velocity vector, also there we see that there are considerable changes in the velocity vector, which we see in this case you have the this way the flow is going the top surface directed, whereas in this case it is bottom surface directed flow is there. So accordingly you can have the feel of the change in the flow configuration. You can also see the velocity vector at the bottom wall. So as you see that in the case of bare Tundish it is going like this, but in the bottom wall you are at the bottom you see the higher velocities up to this zone, whereas in this case you see that this high velocity zone is confined here, because after that it is facing a dam. So it is going up, so velocity is increasing in the upper planes, not at the bottom wall. So as is seen in the case of dam and baffle also. So this is about typically about knowing the fluid flow behavior in a Tundish, and if you do that this is used even to find the different zones inside the Tundish, like dead zone, plug zone or mixed zone or so. So that we will see in our coming lectures, that how we compute these mixing parameters and different Tundish volumes inside the Tundish. Thank you very much.